Hi, happy Pi Day. It's my pleasure to introduce Connor Paddock, who is currently a postdoc in the Department of Mathematics and Statistics at the University of Ottawa. So he earned his PhD here, so happy to have an alumni coming back. His research focuses on the intersection of quantum information science, complexity theory, and operator algebras. And he is an expert in the area of non-local games. He'll be telling us about that today.
Thanks very much, Sam, and thanks to the department for the invitation. Oh no, already gone to sleep on me once. I'll have to go faster, but I already feel like a bad mathematician because it's Pi Day, and I didn't even realize this when I was preparing my talk. So I don't have any good pi jokes or pi puns in here, but pi appears one time, I think. So at least I got it in there once. But yeah, so I was a PhD student here. It's very, ooh, that wasn't me. Okay, it's very exciting to be back and giving a Tutte Colloquia. I saw, a bunch of fantastic talks when I was here. So I'll try my best to live up to that. But today I'd like to present some really exciting work that I recently did with some collaborators, Alexander Kulpi, Giulio Malavolta, Simon Schmidt, and Michael Walter. Everyone except Giulio and I are in Bochum in Germany, this CASA cybersecurities and the large-scale adversaries, and Giulio is now at Bocconi University in Italy, and as mentioned, I'm at the University of Ottawa. So we have a preprint of our work. It's been out for a couple months. So I want to kind of try to motivate, because it's a colloquium, kind of what I'm talking about and the problem that we worked on and we solved. So I hope this part is at least understandable. So in the not too distant future, one can imagine that the most best qubits company, you see a banner online or on Stack Exchange or something, is selling monthly subscriptions to remote access to their latest 10 million qubit computer. And you go, whoa, I didn't know I could get access to such a computer like that. You think, this seems too good to be true. I've never even heard of the most best qubits company. And are qubits qubits? Is that the same thing, or like trademarked, or is that like, some kind of marketing gimmick? But they have a 7-day free trial, and you're like, great. I can click on that, put in my credit card number, and just, I'll remember to, cancel before they start charging me. But then, you kind of get access to this thing, and you're kind of playing with it. I don't know, you kind of put some circuit together, and you have it run. And then you think, well, wait a minute. You remember your kindergarten lecture with Dr. Richard Cleve, and he told you, quantum computers can be simulated by sufficiently powerful computers. And what if this thing isn't a quantum computer at all? What if it's just some machine? So what I'd really like to do is come up with some tests, devise some test for checking if this computer is actually a quantum machine. Can it actually behave in a way that's quantum and not just classical? So I need some test for quantumness. And I remembered too in my lecture from Dr. Richard Cleve that Shor's algorithm is an efficient polynomial time algorithm for factoring numbers on a quantum computer, and we don't know of an efficient one for classical computers. So what if I ask it to factor a really big number? If it's really a quantum machine, then I'll get an answer. But if it's just some supercomputer server, hopefully this problem is intractable. The servers just melt, and I get some computational timeout, and I start to get really skeptical of the most best qubit company. But if you're really, really worried, maybe these guys actually have a classical top secret factoring machine, some proprietary factoring algorithm that's unreleased to the public. No researchers know about it. It's not quantum at all. It's just a factoring machine. Well, it's very unlikely, but it's possible. So you can't really rule it out. And more technically, the point is that this factoring problem is not universal for BQP. So it's not even a problem that we think is, really characterizes the power of BQP, which is kind of what the class of problems that a quantum computer could effectively solve. What we really want is a test for this BQP sort of thing. So we've kind of seen that this thing is maybe a bit trickier than we set out. Really, if I have some quantum computer, if I have access to it, a way to send messages as a classical verifier, can you convince yourself that you're actually interacting with a quantum device, quantum computer? So this is a very fundamental question. It's been around for a long, long time. And I want to tell you about two approaches, one more kind of in-depth than the other. So one of the first kind of breakthroughs, well, that comes from something really, really amazing about quantum mechanics is that so-called these Bell inequalities. So these, we know that fundamentally there are these inequalities where if you have two quantum kind of devices or provers, they can create these correlations that can't be simulated by any classical machine, provided that they're separated and non-communicating. So this would be a way where if you're interacting with some quantum device, you could have them, feed them the inputs of the Bell scenario, and then they could kind of spit back these answers, and you could kind of verify that they're actually producing a correlation that's impossible classically. So this is the kind of non-local approach, and to kind of convince yourself that you're interacting with a quantum device. And this has got a lot of study because I haven't had to make any sort of assumptions about the device at all. So this is sort of, they call it information theoretic or device independent, this thing. So that's a very nice property to have for something like this. Like you can treat the device as kind of a black box. You don't have to make any assumptions about it. You don't have to go and inspect it and make sure that it's a dilution fridge and it's got all sorts of shiny gold wires like you've seen the pictures. But some of the disadvantages of this approach are that the Bell scenarios or these non-local games, which we'll get into, they require kind of two spatially separated devices. So you can't just have one quantum computer, you need kind of two, and they need to be separated, and you have to ensure that they're not communicating with one another. So if the most best qubit company, I just have to trust them basically that they're not communicating, or I have to kind of devise some complicated light cone argument to ensure that they're not sending messages to each other. It would be really nice, like we could save ourselves a lot of kind of trouble. It'd just be a kind of a clean model if we could just have, if we could just do this while interacting with a single device. So I have a single prover and just interact with a single device. And you might think, well, this is kind of the first problem you told me about, and quantum mechanics can be simulated by a sufficiently powerful computer, so you can't really hope to do this exactly, but it turns out that if you make some computational assumptions, this was a huge breakthrough work by Urmi Mahadev in 2018. Well, I think she was a PhD student. She showed that this sort of task was possible if you make some sort of computational assumption. So I think in particular, it was a cryptographic assumption that solving this LWE problem remains hard for quantum BQP machines. And so you might wonder, well, okay, what's this whole talk about if you told me, this stuff about non-locality, but then, Urmi Mahadev almost, 7 years ago has already kind of solved this problem. Well, I think fundamentally what I find most interesting about this area of compiled games is it sort of describes in some way a connection between these two approaches and allows us to kind of understand an area that kind of has felt like for a long time the research has diverged in two directions. This non-locality approach is always appeared very, very different than this sort of line of this computational assumption approach that culminated in the work of Mahadev, but there was 10 years of work before that was sort of like approaching things by using. So first they started by verifying quantum computation with a weaker quantum device, and then they progressively weakened the assumptions that the verifier had, and eventually got all the way down to this one. And it wasn't clear at all kind of how non-locality played a role in these sorts of arguments. And this question of like whether there's a way to bridge these two things has been kind of I think is a very interesting question, and I think that our work kind of takes a step towards that. So I'm not going to talk too much about kind of Mahadev's approach, but instead about non-local games, because that's what I know most about. So we're going to do a little bit of a kind of reviewing of what a non-local game is. So a non-local game is a scenario between two players and a referee. It's usually described by this tuple of some verification predicate, some probability distribution over sets of inputs or questions and sets of outputs or answers. And the idea is that the referee samples questions according to some distribution, and then he hands them to the players. And then once the players have these, once they're given their inputs or questions, they can't, they're not allowed to communicate anymore. So there's some kind of non-communication barrier here kind of set up. And then they kind of, they do something to come up with their answers. So, the simplest kind of thing could just be like a deterministic strategy. They just have some function that when they're given X, they output outcome X sub A or something like this. And what they're trying to do is to kind of satisfy this winning predicate. So this big function has a table, like a truth table of values, where if it knows that if I give questions X, Y, I'm expecting to see answers A, B, and if that thing's 1, then I win, or if it's 0, then they lose. So what the players are kind of trying to do is, given an instance to such game, they're trying to maximize their winning probability. And I write these P, A, B, X, Y's here for these are the probabilities or correlations that kind of arise, because this is all that's kind of the verifier. This is all the information you're kind of seeing in the game is characterized by these sort of correlations. This winning probability is just some linear functional, applied to these kind of this set of correlations. So to understand how the strategies work, we really want to understand kind of like what kind of distributions can they create given different resources. Any questions about this? Hopefully people are still along for the ride. Okay. So I'm going to formally define 2 types of strategies for the games. The first one is where the point of non-local games is to understand what happens in kind of the quantum setting and then the classical setting. So in the quantum setting, they share this quantum resource, but in the classical setting, we're imagining they don't. So here, although it's classical, they're allowed to kind of share this shared randomness or kind of coin flipping that they can use some extra correlations. And these are kind of like, if the deterministic strategies I told you about earlier were kind of these functions, then this kind of allows them to kind of interpolate between these deterministic strategies. So more formally, we model the strategies by kind of 2 collections of probability distributions. So they can be kind of weighted or affected by this kind of shared gamma distribution. And we say that, so these correlations that appeared earlier, we say that they're classical correlations precisely if they can be kind of expressed or kind of written as this way in terms of 2 kind of classical marginal distributions and some kind of shared randomness. However, in the other case, in the quantum case, the provers or the players, what they have is their strategies are represented by when they have, when they're spatially separated. Quantum mechanics tells us that they have separate finite dimensional Hilbert spaces, and the shared quantum resource they have is a quantum state. So this is a unit vector in the tensor product of the 2 Hilbert spaces. So in particular, this thing could be entangled. It might just not be a product state is something that factors into a pure state or a vector here and a vector here, but this thing might not have such a form. Like it could be an EPR pair or something like this. And then the generalization of those kind of distributions I mentioned in the quantum case are given by these quantum measurements or positive operator value measures. These are collections of positive operators that sum to the identity, and they're labeled by questions. So you have a POVM MXA for every X, and each of those, when you sum them over the outcomes A, that gives you the identity. So you actually have collections of these. And they act locally on the first tensor factor, and they don't affect the other one, and then vice versa for these other ones. And the point is here that the probability distribution that the correlations that they can kind of generate are represented by this expression with the inner product here. And if this state is unentangled, then if you kind of do a few lines of math, what you can get is you can actually show that thing will give you exactly a classical correlation. So that any correlation that can be written like this is a quantum correlation. And when we look at these two different sets and we look at the maximal winning probability of the game under each set of correlations, the optimal probabilities under that class are called the value, the quantum value, the classical value. and so on and so forth. And so I've told you about how these two different types of values for the game, so this is the classical value and the quantum value, and we know that they're different because of Bell's famous result. But there's other classes of values, one of which is called the quantum commuting operator value, which is a class of strategies that I didn't mention. And there, it's if we notice in this case, in the quantum case, because the measurements act on distinct factors of the tensor, they commute with each other. But so more generally, you can actually model correlations on an infinite single-dimensional Hilbert space, or on a Hilbert space that's infinite dimensional, where you just demand that the operations be commuting, and you don't actually enforce a tensor product structure. And in finite dimensions, they're the same thing, but if you allow more general classes of strategies, you can get other values, and it was actually, it took a lot of work, but this is a huge result of Xi, Natarjan, Vidic, right? And you in the MIP star equals RE paper, they show that these two values are actually different. And then I mentioned this non-signaling value, which is another value where you can kind of devise these mathematical strategies that satisfy a non-signaling property, but they don't really factor into marginals like a classical correlation would. And in fact, they don't even, it was shown by Popescu and Rohrlich that the non-signaling correlations are actually contain the quantum ones as well. Yeah, sorry. Pardon?
Wasn't it serial 7?
That there was this one here?
No, that they gathered to the non-signaling value and the committing operators.
I'm not sure if it was Cyrilson who proved that.
So you definitely proved the point upper bound with that with the secret given?
Right, maybe. I'm not quite sure. Yeah, so there's these different values that come from different types of correlation sets, basically. Looking at different maximizing that linear functional of those different correlation sets can give you potentially different values. And we know that there are games for which all these values can look different. So let's look at an example. So a famous example is the game of Klauser-Horn, Shimonian Holt, the CHSH game. That's where a referee selects, just the questions are just single bits, and they're selected, here, let's just imagine uniformly at random. And the players, their outcomes are just also single bits. And like before, they can't communicate, but here the winning predicate is specifically given by this kind of this function here. So it's going to be 1 if and only if their answers mod 2 is equal to the product of the bits of their questions. So for instance, if the right-hand side is 1, 1, then one of them has to answer with a 1 and not the other. Otherwise, they would mess things up. And it's not too hard with a little bit of sitting down and some pencil and paper to work out that no classical strategy can win with a probability greater than 3/4. So you can't really do better than kind of just answering one of them always answering 1, and there's a number of inequivalent strategies that get this value, but you can't do any better. However, kind of surprisingly, it's not too crazy. The quantum strategy that beats this does so with just a quantum state on a 2x2 dimensional space, and it achieves a value of, there's my pi for pi to a, cos squared pi over a, which is roughly 0.85. So beating this by about 0.1, 10% increase. So it's substantial. And yeah, so this is the first, one of the most prominent examples of a non-local game where you see a difference between the classical value and the quantum value. So this is kind of the quantum advantage. So this is a way that we could maybe, if we had 2 quantum devices, we would be the referee, the verifier. We could kind of play this game, and we could, be convinced that they must have some kind of quantum capabilities, and in fact, are actually using entanglement. So that's kind of the next thing. So the CHSH has this amazing property that it's not just a test for quantum advantage. It's actually something called a self-test. And what that means is that not only is that value that I told you was achieved, it's actually the optimal winning value. So there's no better strategy, quantum strategy, that does this. This is kind of non-trivial to prove. In general, like for other games and other correlations, quantum correlations, there could be many different models that give you, or many different quantum strategies that are different that give you the same correlations. But for this CHSH winning correlation, it's essentially, there's essentially a unique quantum strategy. Now this is up to some sort of notions that I'm not going to get into, but effectively it's saying that there is a kind of a unique quantum model or unique quantum strategy for winning this game, and anybody who wins with this optimal value will be employing this state and these particular measurements. So this is very powerful. This is a very kind of remarkable feature and a very important feature for a lot of protocols that use non-locality or non-local games as part of their construction. Yeah, so famously, like I mentioned before, that self-testing is the key ingredient that allows for this non-locality approach to be kind of leveraged in the classical delegation and verification of quantum computation. So this is just one of the works. There's a series of works that does this progressively better and better using different games and different constructions for getting better qubits and stuff, and making them kind of robust against small amounts of noise and such. Right. So now let's get to the kind of new technology or new aspect of this work called the compiled game. So remember that in the compiled game, we want to solve this problem that in the non-local game, there's two provers who are spatially separated, and we kind of want to make them one. So what could we do naively is we could just stick them together. So we have our prover, which was our two players. Now it's just one player, and we have our verifier. And let's just have the one player play like both players. But this is obviously going to be a problem. Like, we want to show that this model is effectively the same as the non-local one, and this is going to be be hopeless, because of course what the prover can do here is he can just hold on to X, and he can just keep it for later, and then he has that information for when he's going to answer Y. So the whole thing that makes non-locality and makes non-local games work is the fact that they have this separation. They can't communicate with each other. If I'm a player and I'm playing CHSH, I see my question. I don't know if the other player, if I get 1, I don't know if they got 1 or 0. So I don't know if the product of my number with their number is going to be 1 or 0. So I don't know how to answer 1 or 0 in the game. So in particular, like, although if the game is in this kind of 2-round structure where I first ask it the first question from the game and then the second question, obviously this first player can't do anything that depends on Y because they don't even know what Y is. They haven't even been given Y. But in the second round, of course, they can just use the fact that they've already known X to win the game. I mean, I'm harping on this, but it's really kind of so obvious here that this is going to not work. So we have to be more clever, or someone else is going to be more clever. I didn't come up with this. So the really clever idea is to use cryptography. And this is what Kalai, Lombardi, Vaikuntanathan, and Yang did in 2023, was they took this non-local game and then they added this cryptographic element to it. And in particular, what they do is they picked an encryption scheme as part of the game. So part of the compiled game is now this encryption scheme. And they're going to encrypt the questions and send those to the prover. And then the prover is going to somehow answer kind of in this encrypted thing. And first of all, you're like, well, wait, how is this going to work? If it's encrypted, like, how can the honest prover implement their quantum strategy on some piece of encrypted data? And to solve this problem, we use a very, very powerful cryptographic, they suggested to use a very powerful cryptographic primitive called quantum homomorphic encryption. And I can hopefully summarize quantum homomorphic encryption in this small diagram here. And the point is, if I start up here and I want to apply some quantum circuit, so we're imagining that my measurements, the whole behavior of my quantum device, its measurement, so it's getting X, it's running some circuit, and then it's outputting its outcome. That's some quantum circuit. And the point of quantum homomorphic encryption is that we can agree on some scheme, and applying the circuit, encrypting, is the same thing as encrypting and then applying this circuit. And so what this allows the prover to do is actually run their strategy for the game that they would in the honest case under the hood of this homomorphic encryption. So although they're never going to see what X actually is, the correctness of the quantum homomorphic encryption scheme is going to guarantee that it would kind of, like when they decrypt alpha here, it will genuinely be the outcome if they'd applied the circuit in the kind of without the encryption. And because we act in 2 rounds here, we only need to hide X from the prover. Because once they've kind of answered and then kind of sent their encrypted answer, we can just send the next one in the plane here because we're not worried about them. They can't go back in time and use that to affect their answer earlier. Any questions about this part in particular? Yeah?
Is the alpha being sent back also encrypted?
Yeah, so they have to, yeah, exactly. So they have to run, the verifier is going to run a decryption algorithm on this alpha to kind of get the A. And then this is just the regular predicate from the game before. So yeah, this is the description of their compiled game. So 2 things to note. We have to give up something. So we've you know, what do we have to give up? Sure. Yeah.
Who knows the key of these encryptors? Suppose prover and verifier.
No, just the verifier knows the key. Yeah.
So okay.
Yeah. So that's the beauty of the beauty of homomorphic encryption is that they never have to decrypt at all. No decryption until so the prover never decrypts anything. Yeah. So we have to give up something though, because these quantum homomorphic encryption schemes, they depend on cryptographic assumptions. In particular, we have to now assume that our prover is computationally bounded, so that any strategy they employ can only be achieved by quantum polynomial time algorithms. If we give them more time, they could break the encryption scheme. So why is this going to work, though? I mean, we haven't really said why this kind of, this intuitively why this is going to simulate non-communication. And what we'll see is that the properties of the quantum homomorphic encryption scheme are going to kind of guarantee that, like, no matter what Alice does in the first round, they can't really leave any information in the state left over. Like, if you don't understand how quantum measurements work, they kind of make some measurement. There'll be some post-measurement state. And what if Alice just tried to encode X into some state and then allow Bob to kind of try to perform some measurement and learn X to give him an advantage in the second round? And so what the security guarantees of the QHE scheme are gonna be that these states, these post-measurement states, are computationally indistinguishable. So there's no information that they can kind of gain. And I'll say more about this later. Yeah. So all I'm kind of trying to say is that Bob can't really infer much information about X, and that's what we're going to try to show. So what is known about these things? So there was some stuff known about compiled games. So in the paper that Kalai et al. Introduced these things, they proved several things. In particular, they proved that you can still witness quantum advantage in compiled games. So to do this, they had to prove what's called classical soundness, which just means that any classical strategy for the compiled game has winning probability at most the value you could do in the classical case plus some negligible function. This is a function that's less than any 1 over polynomial in the security. So this is the security parameter of the QHE scheme. As it gets bigger and bigger and bigger, you get more and more secure. So this is something that's achieved that you kind of have to show. So yeah, this is really nice. This is saying that no, like any classical prover for the compiled game can do no better than classical provers could in the non-local setting, where they have no quantum entanglement. They're just non-communicating, up to some negligible amount. So if lambda is really big, then this is great. But you also need to prove quantum completeness, and this comes from the correctness of the quantum homomorphic encryption scheme, because it says that I can take a quantum strategy in the non-local game and I can compile it. I can put it through this QHE scheme, and I can do at least as well in the compiled game. So if I have these two properties, I can and I make this extra little bit small enough, then if I have quantum advantage for some non-local game and then I compile it, I'm going to kind of see I'll have some quantum advantage in the compiled setting. So it's pretty cool. But one property that that KLVY wasn't able to show is if we're fundamentally interested in ensuring that this compilation procedure not only can kind of guarantee this quantum advantage, but does it really, is the prover here really fundamentally constrained by quantum mechanics, like in the non-local case, right? So quantum soundness here is saying, well, I could be concerned that the prover could somehow do something using some quantum ability to do better than the quantum provers could in the non-commuting case. So right, it's kind of confusing because in both cases I'm talking about quantum provers, but in one case I'm talking about two non-local devices, and here I'm talking about kind of one device. So this was kind of this was the left open, and the motivation for why we need this quantum soundness is, well, if we really want to apply these self-testing protocols, and a lot of these protocols that use non-local games, a lot of them use this self-testing for verification or delegation. And without self-testing results, how do we actually know that, without quantum soundness, we can't really bridge these results into the compiled setting? Because maybe there's some other strategy in the compiled setting that they could be doing that creates, for instance, non-signaling correlations or something like this. Right, like this only constrained the quantum provers, so we need something more. So to do that, we have to kind of get into the nitty-gritty of kind of what a compiled strategy is, and kind of start to break down and look at the correlations that are being produced by these provers. So this is I'm going to give you guys the first definition of a quantum strategy for a compiled game. And this one is sort of the starting point for looking at kind of how we can kind of come up with a bound on the value of the compiled game. So it's fundamentally two algorithms, right? Where the first algorithm says, I get some ciphertext from the encryption, and I apply some circuit according to lambda to some state, or some register with the question encrypted in it. Maybe I'm allowed to have some extra qubits around there so that this is a unitary. I perform my circuit, and then I kind of I spit out this outcome A. And then secondly, they're going to kind of get some Y and some other register, and then they're going to apply this circuit W sub lambda, along with this, right? They could be fundamentally. Nothing says that they kind of have to do anything to the register they had before that was kind of had their encrypted answer, or the resulting algorithm applied to this would be the post kind of measurement state. And again, they kind of spit out some outcome B. And this is sort of a requisite definition for satisfying the properties that kind of, well, I said quantum polynomial time prover. Well, then their strategies need to be QPT algorithms, so I have to kind of do my due diligence and make sure that these are actually QPT algorithms. And to actually be, note that they're kind of, I need to be a valid definition for the security and to fit the bill of the quantum homomorphic encryption scheme, I need to have a method of working for every single security parameter. So I can't just pick a security parameter and work in that. I have to be able to do this kind of for any. But this isn't very useful for fundamentally understanding the correlations that are being produced by these devices, by quantum polynomial time provers in the compiled setting. So it's much uglier, but also necessary to kind of look at the correlations that they're producing. So we can unravel those algorithms I mentioned, and we can look at, for instance, the probability of outcomes A and B given inputs X, Y at a chosen or at an arbitrary security parameter. And what this does is we can see that they have kind of really fundamentally what's going on is they have some states and they have some quantum measurements, and we see that they kind of look like when I wrote down the quantum correlations from before, these kind of almost look like them, but I have all this annoying junk around from the fact that I have to use encryption schemes and I have to encrypt with keys and all this stuff. So to make our lives a lot easier, what I'm going to do is I'm going to take all this red stuff and I'm just going to write it, because it all only depends on X and A, and I'm just going to stick it all into this sigma lambda XA. And so this sigma lambda XA is not actually a density operator, meaning it's not a trace 1 positive semi-indefinite operator, but it's less than 1. And in particular, if you sum over A, then it will give you a density operator, so a trace 1 state here. So this is a bit nicer. It's a bit nicer just to have an expression where we can kind of look at these. But note that because the Bob operators, I'm calling them Bob operators, but they're just the measurement operators that occurred in the second round, they could just stick around because they're kind of in the plane. It's kind of neat that they kind of survive through and they're kind of just there. So, but the point is that this thing a priori doesn't look like a quantum correlation. Doesn't look like that one, and I showed you that slide, the definition of quantum strategies, and I said a quantum correlation needs to look like, something like, PAB XY equals some inner product with some, I don't know, maybe I had some AXA tensor BYB. It doesn't look like that. It doesn't even look like a quantum commuting operator correlation, which is one where I just had some product there. Now, if somehow these operators, these measurements that are being applied basically under the homomorphic encryption, if they commute with the B's, then I would actually kind of be able to say, oh, hey, these are just quantum correlations. But I have no reason to kind of, there's no reason a priori why that should be true. Okay. So, but going over this way makes, gives me another definition of quantum polynomial time strategies that's a little bit, I don't know, it's more friendly mathematical, and it brings it closer to things that I've seen before, maybe some of you have seen before. So we can write more advantageously a quantum polynomial strategy for a compiled game as this family. So for all these security parameters, it's really just a Hilbert space or a series of Hilbert spaces, vector states, these subnormalized densities, and these POVMs. So to kind of hopefully bring this down to earth somewhat, when we look at these strategies, I wrote this thing before, so it's not quite a density operator, but it encodes the probabilities that if you just look at the marginals, so you sum over B, then you get the probability of A given X, and it's just represented by the trace of this density, or subnormalized, of positive contraction. And the probability of B given Y is given by this expression. Now, it depends on X, and that's kind of the whole problem, really. So if there's this expression right now is currently depending on X, so that's fundamentally a sort of an issue. But I want to note that this expression here is something called a state. It's a positive linear functional. And this is a very important object in C-star algebras. And in particular, this guy here is a state on the C-star algebra generated by Bob's measurements. So that's just, if you look at polynomials, non-commutative polynomials in these operators, and you allow adjoints to be kind of stuck wherever you want, then this thing generates a kind of, if these are finite dimensional, then there's a matrix algebra, and this thing is a state on that matrix algebra. Okay. But I want to fundamentally, so if I want to prove quantum soundness, what I want to do is fundamentally bound the so-called compiled value of the game. So what is the compiled value? If we want to bound it, we need to kind of write it down. So we kind of define in our paper a couple different values, but this is the one that's kind of the most important. So we call it the Q max of the compiled value. And it's the supremum, which is what you almost always use when you're writing a value, over all quantum QPT strategies for the compiled game. And remember that when I had a strategy, I had to have one for every single security parameter, which means that I actually have like a sequence of these values. And I want to look at the largest one, so I want to look at the lim sup of each of these values. And I'll define my quantum value to be the sup over all the lim sups of the QPT strategies for lambda. And maybe this is a little bit cumbersome, but the point is that if I have an upper bound on this value, it means that no quantum prover can exceed the acceptance probability lambda by any constant for a large enough security parameter. So this is the point of writing it like this, is that I can basically kind of say this thing that makes more sense to us as humans. So fundamentally, giving some bound here would be great. So what we want to do is we want to bound this by the quantum value. That would be what quantum soundness would be, was bounding this value by the quantum value of the kind of original uncompiled game. And I'll mention that there was some previous work that did this in special cases. Natarjan and Zhang did this for the CHSH game, and then enabled them to kind of do some really interesting things with that. And then there's some work with myself and like many collaborators, combined papers, and other people with the same result a few weeks later. So we were able to kind of bound specific families of non-local games, but we didn't have the methods for kind of extending these to all non-local games. And actually, the proof method we have here is fundamentally different than the ones used here. But I can say more about this after, because there is a reason why these ones are maybe better in some sense. Okay. So to get our bound, we need to revisit those cryptographic assumptions that I mentioned at the very beginning. So why does cryptography enforce non-communication? Because non-communication is what's giving us the quantum value. So how is the cryptography giving us the non-signaling or non-communication? And the starting point is this kind of a proposition that you can kind of fairly easily prove about the security of the QHE schemes. In particular, it says that if you take any x and x prime, so you pick up a pair of questions, then there exists a negligible function that bounds kind of the expectation of these like probabilities. So you can't really distinguish between if you have kind of x or x prime here. So no quantum polynomial time distinguisher can differentiate between kind of this sigma x density or sigma prime x or sigma x prime density. So in some sense, I mentioned that these probabilities, these probability PB y, they sort of depended on x. See, these ones depend. This is the probability of b given y, but there's some x dependence here. But here, what this is saying is kind of like, well, but you can't really detect the x dependence because the x dependence just looks like the x prime dependence. So if these were all the same, then it's really like saying, well, it's like being independent of x entirely. So as the security parameter gets bigger, Bob has less and less signal. He can kind of detect less and less information about what x is, which is going to kind of, that's exactly what we want to recover the compiled value or the non-local value. So what we do is we study these games in the limit. So we look at an idealized situation. When you can't solve the problem, you kind of look at it, you make it easier. So we look at these so-called sequential games where we don't have any cryptography, but we restrict the class of strategies we have. So we saw the class of strategies that was allowed in the compiled game. Now we want to look at the class of strategies that's allowed in these sequential games by looking at an idealized version. So instead of saying that the states are kind of indistinguishable or nearly indistinguishable, we're going to say that they're actually just all the same. So you can't differentiate between them. They're all just the same states. All these things are the same. So, and we call this property strongly non-signaling. And the question is now, well, what correlations do you get if you have strongly non-signaling? How much time do I have? 5 minutes. Okay. So what we have in this situation is kind of one of the first what you can show is that the correlations you see in this setting, if I restrict the finite dimensional, these so-called strongly non-signaling strategies, which are like an idealized version of the compiled ones, the resulting correlations are just the quantum correlations. So we get exactly what we want in this. So that's our kind of first thing. And actually, when we did this proof, we actually later, it was pointed out to us that there was actually some earlier work by Nevezquez, Cooney, Perez-Garcia, and Villanueva in a paper back in 2012 that I don't think didn't get much enough credit, but they kind of noticed this same feature phenomenon kind of 10 years before. So I was going to go over the proof, but I'm kind of low on time here. So I'll kind of just skip kind of over it kind of quickly here. It's kind of neat. It uses some ideas from purifications, uses Ullmann's theorem, and to kind of construct quantum measurements. And the punchline is that basically when you look at when you have this property of strongly non-signaling, you can use these purification arguments and Nymark dilations and then these theorems, basic theorems in quantum information theory to kind of build up the finite dimensional strategy, and at the end of the day, conclude that the correlations you see at the end of the day are the quantum correlations. So it's kind of really neat. But unfortunately, this result is too weak for our purposes of bounding the compiled game. In particular, even if we take computational non-signaling, it doesn't imply this strongly non-signaling, even in the limit. So remember that was like saying that the sigma x was equal to sigma x prime. The densities were exactly equal. But if you recall, the strongly the property that was being enforced by the computational indistinguishability wasn't about the closeness of these densities being kind of all the same thing. It was saying something about the linear functionals, the states, the trace of that operator against Bob's measurement operators. So we needed something a little bit stronger. And so to do that, we look at something called an abstract strongly non-signaling strategy. So this is also in the sequential game case where I have no cryptography. But now, instead of just allowing strategies that come from concrete density operators, I allow arbitrary or kind of abstract linear functionals on some potentially infinite dimensional spaces. So not every state can be written as a trace against a linear functional in the broader mathematical theory of operator algebras, but it's merely an example of one. So nonetheless, you can kind of consider these strategies mathematically, and what we showed was that they give you the quantum commuting operator correlation, so that bigger set of correlations I mentioned at the very start when I was talking about values. And the shift to doing that employs actually a very similar proof techniques to the ones I skipped through kind of quickly on the last slide. It just uses some kind of C-star algebraic machinery instead of the kind of more conventional quantum information machinery. But it's kind of just kind of some beefed up version of that kind of stuff. And so with that result in hand, though, this result that's a bit stronger, and maybe it's unclear why we need to go to this case with these abstract states. Yeah, maybe I'll try to get to that. But the kind of punchline was, with this result in hand, we were able to show that the quantum value of the compiled game is in fact not bounded by the quantum value, but by the quantum commuting operator value. At least we don't know if it's bounded by the quantum value, but we could prove that it's bounded by the quantum commuting operator value. So in particular, we have that for a large enough security parameter, note that we kind of can't say anything about how big we need it to be. It's an asymptotic statement. But no quantum polynomial strategy can win the compiled game with a probability exceeding the quantum commuting operator value of the game by any constant. And the proof technique is kind of, hopefully kind of what I've kind of allured to so far. It's to use this computational indistinguishability to show, but in fact, instead of getting, like I said, strongly non-signaling, we actually get abstract strongly non-signaling. And that's because when you look at the asymptotics of this quantum polynomial time distinguishing idea, you get a convergence on the level of states and not a convergence on the level of density operators. And so when you do this, you kind of are, you know that you have some convergence to some abstract state, and this thing might give you an arbitrary quantum computing operator strategy. You don't know if it's going to be a quantum strategy. But to handle the technicalities of the fact that when you're looking at the states and observables in the Hilbert space in the compiled strategy, they can be various dimensions. They can be bigger and bigger. They can do all sorts of things. There isn't one space that they all live in for each security parameter. You have to kind of find a systematic way of putting everything into one space to make everything work, to talk about this limit. And fortunately there we can use some more operator algebras. In fact, we can use this kind of universal property of this C-star algebra that kind of represents on some fundamental level all the quantum measurements that you could kind of make. And there we can kind of make all this argument rigorous. So yeah, you can see the details paper for that. Our result, so from our result, we can take this now to give us an application to do kind of self-testing. But because we didn't get a bound on the quantum value, we have to kind of adjust our notion of self-testing a little bit different. Conventionally, people talk about self-testing in the quantum, in the framework for quantum correlations, using the language of local dilations. But it's sort of, we don't have a good understanding of what that means in the context of computing operator correlations, because we don't have local Hilbert spaces in that model. There's just a global Hilbert space. Fortunately, this comes back some work I did during my PhD with William Slofstra and Yuming Zhao and Yangchen Zhu. We showed that there are these kind of this natural notion of commuting operator self-tests, and if you're a self-test in the, and we showed that a lot of self-tests in the quantum model were also self-tests in this commuting operator model. And this allows us to kind of apply our soundness for quantum computing provers in the compiled setting to give us self-testing results in the setting of commuting operator correlation. So this slide's a bit for the experts here, but it's maybe at the bottom I can kind of illustrate a cute example, which is, for instance, in the CHSH game, we can conclude that the plus minus one valued observables are like the poly X, poly Z operators that are being applied. In any optimal compiled strategy, they must satisfy this fundamental anti-commutation relation. And this is kind of the building block for a lot of self-testing protocols, is once you have kind of anti-commuting observables, you can start to construct EPR pairs and such things from. So it's it looks like a big scary thing, but it has it kind of recovers what we'd expect to see in this setting. So in summary, our results are some of the first quantum soundness results for all non-local games or Bell scenarios. As an ingredient, we gave an alternative characterization of quantum computing operator correlations using some, I think, interesting connections with cryptography and using tools from operator theory and cryptography. I don't know too many other examples of that. And our results kind of enable fundamentally some kind of self-testing in this compiled setting. And I think the whole point of this compiled setting in my mind is that it kind of provides us with a modular framework for looking at protocols for delegating or verifying quantum computing, where we can work in this non-local model that's a lot more familiar to a lot of us, where we have Hilbert spaces that are tensor product, and we kind of understand a lot more what entanglement is in this setting, rather than these sort of maybe more ad hoc constructions that kind of just use really complicated and ingenious cryptographic tools like the protocols of Mahadev. And so by focusing on this, we can just develop we can focus on information theoretic protocols, and then we can turn them into computational ones via the compilation procedure. Although we were really happy with kind of proving this fundamental bound on the compiled value, there's a lot of interesting open questions that are kind of left by our work. The first one is that our result characterizes the kind of how what the set of compiled correlations, if you like, looks like in the limit. But what if you just want to take some big enough security parameter, or kind of we don't have any sort of result that says at some finite parameter, do those look epsilon close to quantum correlations? That would be the next step, is kind of proving some sort of quantitative bound. And this comes back to, I mentioned those other results that we have for the class of XOR games and a few others. Those results actually give quantitative bounds. Hopefully there's a meeting point between these two approaches. Secondly, we fundamentally don't know if QC really is the tightest upper bound. This is kind of, I think, a very interesting maybe question. Could more refined methods give you the quantum value if you kind of came up with some more ingenious in-proof techniques? And the last big question is whether can we do away with the quantum homomorphic encryption and come up with some weaker cryptographic assumption for compiling games? The point of this is that fundamentally quantum homomorphic encryption is a very strong primitive, and it actually allows quantum messages to be sent. But in the compiled game, the data that's being sent and received from the verifier and the prover is all classical. So we already know that we don't need the full kind of power. And actually, there was some recent work done by my co-authors, and they had a follow-up work where they, in fact, were able to kind of show that you can do a compilation procedure from any trapdoor claw-free function. So a seemingly weaker claw-free function, TCF, yeah. So they kind of use a combination of kind of a blind computation and remote state preparation procedures that just have this certain. So it's like everything in cryptography. It's a seemingly weaker assumption. We don't know how equivalent they all are. But I think it's a very interesting question. What can you get away with for compilation? And that's all. So thanks very much.